दिख रही है ना?
हाँ बस एक बार पीपीटी चला दे।
विजिबल है?
हाँ विजिबल है।
ठीक, ओके।
Okay. Good afternoon to one and all. Myself, Dr. Manish Sharma. I am here to welcome you all for the fourth day of our 1 week workshop on advances in manufacturing. Today, our speaker is Dr. Tarun Bharadwaj. He is assistant professor at Ajay Kumar Garg Engineering College, Ghaziabad. He has pursued his master's and PhD from MNIT Motilal Nehru National Institute of Technology, Allahabad. He has pursued his PhD in the field of laser additive manufacturing. He has published more than 5 papers in international and national journals, as well as 5 papers in the national proceedings. He is being a great scholar in the MNIT. So I welcome Tarun to give his speech for the day. I welcome you, Tarun. Please take over.
Thank you so much, sir. Myself, Tarun Bharadwaj. I am assistant professor at Department of Mechanical Engineering at AKGEC Ghaziabad, and a very good afternoon to all the faculty members and my dear students who are listening to me. So I'm just giving today's talk on the additive manufacturing. That is basically the 3D printing. And as you all know about the additive manufacturing process, it is a very new and the innovative manufacturing process, and hopefully it will be a future for the manufacturing. And if we just talk about the textbooks to the students, that they belong these particular textbooks and the reference books, and now I just introduce these basically what actually happens in the additive manufacturing process. Uh, as you know about the subtractive manufacturing process that are already being uh, processed from the last few years or from the past years, as we know about the subtractive manufacturing process, like the cutting and machining process. But in that particular manufacturing process, there is no wastage of a material, as it is the name suggests that additive manufacturing. So additive is basically means we add a material on a layer by layer manufacturing process. Means first of all we just add a material on a material, and then we add a material a layer by layer, as you can see in that from the first figure. As you can see that there are some layers like a welding, as we have done a welding kind of thing. So these are the layer by layer we just process and make a complete product from it. These are basically the lattice structures, guy rod structures, and these having a very high strength to weight ratio. So we can manufacture by the additive manufacturing process. And first of all, what is basically the additive manufacturing process? The term that you have heard from the last few years, that the rapid prototyping, that is basically being used for the additive manufacturing process, and it is used to describe the process for rapidly creating a system or a part representation before the final release or commercialization. Uh, Means first of all additive prototyping, and after that we just say that we can create or we can manufacture a 3D component. So we just change its name by from the rapid prototyping to the additive manufacturing. Recently formed technical committee by the ASTM International, it agreed with the new terminology should be adopted. Means they first we call it rapid prototyping, then ASTM standards. We just They have just agreed with that we should have to change or we should adopt the name additive manufacturing for this particular process or for this particular technique. And the basic principle of this technology is that a model that is basically initially generated using a 3D CAD system. First means if we have some design in our 3D CAD systems, you can use any 3D CAD software. Suppose you can take SolidWorks, AutoCAD, or NX, whatever you want. These CAD files you can directly convert into a models uh, uh, by using this particular manufacturing process. And prototype fundamentals, if we just talk about then a prototype is basically a first or original example of something that has been or will be copied or developed. As we know about the prototypes, it is a model or a preliminary version. So prototype superchronic craft, suppose, and we have to make a prototype. So we can directly manufacture by the additive manufacturing process. And we just talk about the types of the prototypes. So the general definition of a prototype contains three aspects of interest. The first one is the implementation, second one is form, and third one is degree of the approximation of a prototype. And when we talk about the additive manufacturing process, as I have already told you that it is a layer manufacturing process, and the other terms that is being used for the additive manufacturing process are the additive layer manufacturing process, additive digital manufacturing process, and for the layer, it is the layer-based manufacturing, layer-oriented manufacturing, layer manufacturing, and before that, we are using rapid prototyping, rapid technology, rapid tooling manufacturing process. So they are the different names by different countries or by the different organization according to their suitability. And the name also come after the rapid prototyping, that is 3D printing or 3D modeling, or you can say direct manufacturing or direct tooling. So it depends upon the organization who are working in that particular research area. So according to the suitability, they just suggest the names. And now we just come to the additive manufacturing, that is a layer manufacturing process. As I already told you, that it is a layer-based automated fabrication process. And this automated, why? Because it is use the NC tools for the fabrication process. So we have to
Hello, Tarun. We cannot hear you. Hello.
Okay, so using the whole solid figure is converted into a small layers, and or these layers are basically having some thickness of you can say 40 micron or 50 micron. Okay, and we have to make these small layers and just convert it into a solid parts. And they are just opposed to a subtractive manufacturing process. If we just talk about the CNC machines, so first of all, we have to create some solid object, and then after that, we have to do some machine just to create these products. So this is a subtract manufacturing process, and it will cost us a high. So we have to remove that particular cost. So to remove that cost, we can adopt this technology, but there are some advantages and disadvantages also for any process. So what is actually the cycle of this particular process is that starting from the CAD, first of all we have some CAD design. Means if we have some CAD design from any software, we can just convert it into a STL file. And after that, the file is transferred to the machines, and after converting the file into machine setup, we just go for a build, and we can remove the support structure, because sometimes we required support structures. Uh, support structures are required Support structures are required for the overhanging parts, and after that we have to do some post processing. Post processing depends upon the material, because they are the few materials that are having a strength after these post processing techniques, as you can say HIP or laser shock pinning. HIP is basically the hot isostatic pressing, in which we used to press the material to remove the pores of that particular solid material. And layer shock pinning, it is a you can say basically a surface treatment kind of thing using the laser. And after that, it will be used for the application, and that means we can use it is for the final application, whatever application the product has. And we just talk about the introduction of it, how it starts, how the evolution start. So from the year of inception, means from the 1770, we start with the mechanization, and in the 1946, the first computer we have, and 1952, the first NC machine tool we have. So this technology is developed from there, because it is start from the computer, it starts from the CAD, it starts from the NC tools. So from the 1952 to the 1960, we have the first commercial laser, as lasers are using we are using nowadays the lasers for processing of metals. And for polymers, sometimes we use laser, but as laser are having very uh, their temperatures are very high, so we are basically use laser for the melting the metals. And in 1961 we have first commercial robots, as we are using the robotic arms to move or to for the CNC machines, so we have to use the robots. So, and in 1963 we have the first interactive graphic system, that is basically the CAD. So these are basically that means you can say components of it, means additive manufacturing: CAD, first commercial robot, and laser, NC tool, and first commercial rapid prototyping system comes to into picture in 1988. Means after the development of these so much components, so after so many years, in 1988 we have first commercial rapid prototyping systems. And as we have to how we distinct between the AM and the CSE machining, means the subtractive and the additive manufacturing process. If suppose we have some material and we have to subtract the manufacturing process according to their shape, and even after the subtractive manufacturing process, there are some shapes that we can't get, as you can see in the A and B. So for the A, we have a solid material, and the solid material is machined by some CNC, as written over there, that are subject to manufacturing, and we are getting the 3D object. And after that we get some waste, means the removal of the waste is there. And in the B part, in the B line, you can check that there are a few material. A material can be in any form. It can be in a form of a powder, it can be in a form of a wire, and after that, that particular powder or wire is we just melt it down by using any energy source. For the metals, we are using lasers, we are using electron beams, and for the polymers, we are just using small heaters, because they are having the melting point of nearly 200, 300, 500. So, and after that, additive manufacturing process, we are getting the 3D object plus waste. But the difference is that from the AM and the CNC machining is that we can't get the intricate shapes. If I ask you to make some hollow sphere by the CNC machining, you can't, because there is no way that you can make intricate shape in a sphere. But it is possible that you can make an intricate shape in a sphere. So this machining process is quite useful in that particular way. So what is the distinction between the AM and the CNC machining? That point of view between the materials and the speed, it has a very high speed. If we just talk about the laser speeds, that are quite high, and the ease of use and the accuracy is very good, and size limitation, geometric complexity is there, and we have to do some programming in that, just like the CNC. And it is cost effective, but cost effective not in the terms of a process cost, but in terms of a waste, you can say, because process cost is very high due to the use of lasers, electron beams there, because as you know that lasers are of crores, so the process cost is very high, and they are quite environmentally friendly, because as you know the waste is very low, so they are quite environment friendly. And then we talk about the advantage of AM, that what is actually the advantage. So we have some elimination of the design constraint, because as I have already given example about the intricate shapes, complex shapes, lattice structures. So we have some you can say a constraint for these particular designs, so it is quite difficult by the subtractive manufacturing process or any other process. So we have to eliminate that design constraint, and that can be eliminated by the additive manufacturing process, and it allows the parts to produce with a complex geometry with no additional cost related to the complexity. Means if you just go for some machining shop, so if you just say that I have some intricate or I have some lattice structures, so due to their complexity they will take a more cost from you, so that part will be reduced by the additive manufacturing process. And when we talk about the build speed and the reduction of lead time, the reduction of lead time will be low, because In the subtractive manufacturing process, first of all, you have to buy some solid casted part, then you have to machine it, and then after that you have to post processing it. But in additive manufacturing process, you have a powder, you have a raw material with you, and then you can directly make that product and post process it. And if you just go for the flexibility in the design, so you can you are so much flexible for your design. You can change your design in between also. If you have some you are making some product and you want to change that particular design in between, so you can change it by just coding in that particular in the CNC coding. So there are no expensive tooling required. So dimensional accuracy is very high, and wide range of material you can use, means polymers, metal, ceramics, and alloys. And means you can mix up the alloys, metallic alloys, and you can also nowadays you can also do the composites from these additive manufacturing process, and they are well suited to manufacture of high value replacement and repair parts. Means if you have to repair some part, it is quite difficult to repair the parts. It means if you have uh, some, you can say, cracks in your parts. If you manufacture some part from some process and you want to repair that particular part, so it is quite difficult to repair that part. You have to weld it, or you have to make another part. So by this process you can repair that part, because it is a layered manufacturing process, so you can just make a layer on a crack. So, and it is a green manufacturing process, clean and minimal waste process. And the limitation is also there with that process. The first one is the part size, that we cannot go for a very high part size. There is a limitation. And the production series, they are basically generally suitable for the unitary or the small series, as I told, and it is not relevant for the mass production. Now it is being used for the mass production for the polymer parts, but not for the metallic parts. And it is being used for the small size parts. Series up to 25,000 parts per year are already possible. And materials choice, no weldable metals cannot be processed by the additive manufacturing, and it is difficult to weld alloys, require specific approaches. Means if we just go for the there are the few alloys, and like the an inconel alloys we're just talking about, so it's quite difficult for the by the welding processes. So we can just make a part by the inconel alloys from the additive manufacturing directly, because we are using the electron beam and the laser beam, so they are very high laser power source, very high energy power source. And uh, so we can directly melt it and make a complete kind of a product. And if we're just talking about the material properties, that how much the what property we are getting from the additive manufacturing process. So the parts made by the additive manufacturing process tends to show anisotropy. The reason of anisotropy is that the solidification rate, because they are having the very high means you can say the high temperature, and after getting melts to any product, they will just cool down to a room temperature. So that the difference between that, you can say the thermal gradient, between the very high temperature to the low temperature, for every layer, it will cause an anisotropy in that particular product in the z axis, in the construction direction. So we can also remove that by using some scan strategies, or by using some different build orientation in that additive manufacturing process. And the densities we are getting for each and every material, that is 99.9%. And the problem is that we are also getting some residual internal porosity and residual stress also in this process, because they are very high thermal gradient process. So there may be chance that high residual stress we are getting. We can remove that by post processing technique. We just talk about the high post processing technique later. And the mechanical properties are usually superior to the cast parts. Means the whatever the cast, because we have a very low porosity in that, because cast parts are nearly 98 to 97 98% having density. So uh, they are a chance to crack in the cast parts, and they are but in general inferior to the rod parts, as written over here. So as I told you, the introduction, and these are the 8 steps about the additive manufacturing process chain. The first one, that is conceptualization and the CAD. And the first one is generic AM process. Start with 3D CAD information. Means we have some design, we have to design it in a 3D CAD model. And there are many ways to how to 3D source data can be created. Means if we have some, if we just talk about the SolidWorks, it use the SLD parts, and if you use the CAD, AutoCAD, it may be exported in any other file. The model description should be generated by a computer, and most 3D CAD systems are solid modeling system with some surface modeling components. They have surface modeling components also. Now AutoCAD also have the 3D CAD model in it. Now after that, just generating that CAD file, we have to convert it into a STL file, and STL file is basically derived from the stereolithography. Stereolithography, and stereolithography is nothing but layered manufacturing. Means a small layer, and then after the another layer is just put another layer on it and another layer. So this is basically the about the STL, and STL type. STL is a simple way of describing CAD model in terms of its geometry alone, and it works by removing any constructed data and modeling history, etc., and approximating the surface of model with a series of triangular facets. And when the minimum size of these triangles can be set with most CAD software, means actually what happened when we just to when we have some solid, we just have to convert it into a some small triangles, and they have some minimum size of these triangles, and these triangles size is just set by some CAD software, and the objective is to ensure that the model created do not show any obvious triangle on the surface. Means we do not have any extra triangles, means triangles are joined by each other. We just create the triangles that they will join each other, so that there will be no obvious triangles present in in that particular solid systems. Now, after converting that STL, we just repair that if we have some if we have some defects in that, so we have to repair. And after conversion, we just transfer it to the AM machines, and we have to do STL file manipulation also. And just when the STL file is created, it have directly sent to a target AM machines. Okay, and after that, it should be possible to press a print button and the machine should build the part straight away. However, there may be a number of actions required prior to building the part. First, the first task will be to verify the part is correct or not. And the AM system software normally has visualization tool that allows the users to view and manipulate the part. Uh, uh, Except that, we can directly manufacture the STL file, and we can also convert it into a G codes, and as you know about the NC tools codes, so we can directly convert these STL files into that codes, and the transfer of this AM machine after that STL manipulation. We just talk about the machine setup, that how the machine setup. So there are the different machines available, and the machines are for the polymers also, for the metals also, for the composites also, and these means these STL files are just after the we have just transferred these files to the machine, and this is the work of the machine, that how it will work on it and how it will identify the defects in this uh, particular, you can say, the G codes and G codes and M codes. And after that, these are the 8 steps. These are the basically the application, that how the post processing is done, and after that how we use that product for that, how we use the 3D printing project. Now the main is the classification of the M process, and as I told, the rapid prototyping, additive manufacturing, 3D printing, they all are name are the same, but have some different name according to the researchers they have used. And as we talk about rapid prototyping process, we are just working on the material addition. So it is additive manufacturing. They are having the liquid one and discrete particle one and the solid sheets one. For the liquid, means we are just converting the solid parts or a powder part in a liquid form. Means solidification of a liquid, a polymer, or solidification of an electrolyte fluid, or solidification of a molten material. Means we used to melt the powder into molten material. And discrete particles, we just fuse all the particle by the laser. Means selective laser sintering. Suppose we have some powder having some melting point, but we just sinter them. We just not completed melting down them, but just sinter them by the selective laser sintering process. And we also join the particle with a binder also. And solid, we just talking about solid seeds. So these are now these are not now used in solid seeds, because loam process and SFP process, because they are quite expensive process. Bonding of a sheet with adhesive, it is quite difficult. Means if we have a sheet, then we just bond by some adhesive and then have some sheet again, adhesive by bond. So it is quite difficult to bond a sheet by again and again, and we are also not getting the accuracy in them. So we are just focusing on the liquid and the discrete particles. As I have told you, solidification of a liquid polymer, it is by point, means SL, LTP, BIS. These are the basic process I just told you. And the layer by layer, SGCs, and holographic surface, it is used the HIS. And when we talk about the solidification of a molten material, and we are using the FDM, 3W, BPM. These are the machines, and this SDM. So these are the basic machine. I will talk about them here. And when we talk about the classification with respect to the channels, and as you know about that, a 1D channel, SLA means selective laser. It is a selective laser sintering kind of thing, SLA, and this is twice of 1D channel. Means we are using the two power source for any product. Okay, and then an array of a 1D channel means we can use many power source for that, and this is basically a 2D channel. This is their manufacturing process. Now, liquid polymer systems and discrete particle system and molten material system, solid system. They, except that there are many classifications for the AM process now, just like the direct energy deposition process are also there, and they are now means newly admitted to this classification of the additive manufacturing process. And when we talk about the liquid polymer systems, liquid-based RP system have initial form of its material in the liquid state, and but by using the photosynthesis, means we are using the some photopolymerization kind of thing. So by using that photopolymerization, uh, the liquid is converted into a solid. Means if we have some source, just like in the photosynthesis, what happened that we have a sunlight source and that convert into a life. So we just start with the photopolymerization. This means the polymers are converted into a chains by some source, and so the name suggests the photopolymers, and the process is photopolymerization. It means we just photopolymerize liquids and just convert it into a solid. That process we call stereolithographic process. And the following RP system fall into this category, means 3D system, SLA, and as I told you, the SLA, that is stereolithography apparatus, and SG. These are basically the machine or for the by the different vendors, that are solid grounding curing and the solid creation system, CMET, solid object ultraviolet laser printers, and there are different machines. And when we talk about the discrete particle system, means discrete particles are normally the powders that are graded into a uniform size and shape and narrow distribution, because we have to keep it uniform for proper bonding. Means if we have powder, if we do not, if they are non-uniform, then the bonding between the powder is not good. So we have to keep that proper uniform size and the shape, and the maximum. Mainly, we are using the spherical shape, and the size is nearly about 5 micron to 105. That is depend upon the process. If we are using the selective laser sintering process or selective laser melting process, we are using 5 micron to 45 micron powder size. And if we just talk about the direct energy deposition process, we are using 45 to 105 micron powder size. And the finer the particle, the better will be your product. But there will be problem if the dimension get too small in terms of controlling the distribution and dispersion also. So if something has advantage, it will also have some disadvantage for that. The conventional 1D channel approach uses a laser to produce the thermal energy in a controlled manner to raise the temperature sufficiently to melt the powder. If we just talk about the laser, so they are using mainly 1D channel. Now the 2D channels are also using, means we are also using 2D lasers. And I've worked my research topic, the research areas mainly focused for the 1D channels, but now since 2018 or 19, the 2D channel approach is also used for the lasers. And the polymer powder must therefore exhibit thermoplastic behavior so that they can be remelted and remelted to permit the bonding for one layer to another. Means we can only if we want to do some means 3D modeling for polymers, they exhibit some thermoplastic behavior in them, so that we can melt them or remelt them if we have some defects. So we can remelt them and we can cure them. And two main polymer-based systems that are commercially available are Selective Sintering, and so the second one is the EOS INT, that is process developed by Germany company EOS. I think the company is basically electro-optical systems. And Selective Sintering technology marked by the 3D system. 3D systems is now means it is emerging systems, 3D systems, and it is being largely being used by Indians also, 3D systems. And these are the few machines for the discrete particle systems. And when we talk about the molten material systems, molten material systems are characterized preheating chambers. Means we have some preheating chambers, means have some temperature in them that raises the temperature, material temperature to a melting point, so that it can flow through a delivery system. Means we just melt down the powder, or we just preheat that particular powder to melt down, and that melted part will be solidified into a layer by layer. Actually, as you all know about the welding process, it has some bead. When you just weld some, you can say if you just weld two sheets, so you have a bead between them. So that particular bead, if you just overlap that bead, so that completely makes a single layer. Means if you just make bead layer by layer, means overlapping by overlapping, means if you just overlap one bead 50% with the second bead, the third bead, fourth bead, so it makes some single layer kind of thing. And when this layer is overlapped by the another layer and then third layer, so it will be a 3D printing. Means it start from some welding. Means uh, the approach will start from the welding process. And the most well-known method is FDM, that is fused deposition modeling systems, that is designed by the US company Stratasys, and we have this system in our AKGEC, and we are also planning to buy laser systems that is nearly 4 to 5 crores. So this approach uses an extrusion technique, and that is to deliver the material through a nozzle in a controlled manner. So extrusion, there are some extrusion technique also, means we have wire and we have to melt that wire, and that melted part is to be deposited on a substrate or on any material. The other two extrusion heads are often so that support structure can be fabricated. Means one nozzle is used for the support structure and one nozzle is used for the main part. If we have suppose some polymer, means you just say if we have some polygalactic poly PLA or polylactic acid, and we want to manufacture and want to give some support structure, so we can differentiate that by the colors. Means we can use the white color for the PLA and some red color for the support structures. So we have two nozzles, and we have for that we require two extrusion heads. So this is about the FDM, and the 1D channel approach is very slow in comparison to the other methods, because we are using only one source for that. The thermojet from 3D system also deposit a wax material through the droplet based printing heads. Means the process is same, means layer by layer manufacturing, but it may be different for different material, or so means the companies can use a different approach for that. For the solid systems, as I told, it will be now being used. It not being now being used because of the its accuracy and its cost. The laminated object manufacturing. Here, what actually happens, laser is used to cut out the profiles from the sheet paper, and that sheet paper is used as a single layer. And after that, laser will cut another profile for the second layer, and then for the third layer. And these layers are is bonded by some adhesive, so it is quite expensive for us. So we are not now use these type of systems, solid systems and liquid polymerization. Now we just come to the SLA process in the detail. 3D systems was founded in 1986 by the inventor Charles W. Hull and the entrepreneur Raymond S. Freed, and its first commercial system marked in 1988. And it has been awarded more than 40 US patents and 20 international patents, with the additional patents filed and pending internationally for the SLA, because it is the first 3D printing process that is being developed by the Stratasys. And the principle is this: the part are built from a photocurable liquid resin. Means we have some liquid resin that is photocurable. So we just cure it by exposing a laser beam, and which scan across the surface of a resin. And when we cure it, it just solidified it. And we just solidified it by a layer and by layer another layer, and then we build it in a z direction. And each layer being scanned by the optical scanning system, and it is controlled by the elevation mechanism means in the z-axis, that which lower at completion of each layer. Means if one part is cured, then it will lower down, and then second part is cured, and that elevation mechanism will control the basically the layer thickness. Means we can control that layer thickness by the elevation mechanism. So it is basically the liquid polymer system. Here we have a laser. Here we have some platform, and this, if we have the photopolymerized resin in it, so we just cure it by the laser, and just elevator is used to lower down, or just to uh, make another layer for that particular you can say product thing. If we have some product, and then we have to make some layer on it, so we just lower down by using the elevator. And we have the wipers also, wipers just to remove any extra material in it. And if we just talk about the SLA process, the stereolithography process, uh, it mainly creates 3D plastic projects directly from the CAD data, and the process begins with the wet field, and with the photocurable liquid resin, and the elevator table just below, just to set the below and the up of the surface of a liquid resin. And 3D CAD solid modeling file is loaded into a system by the operator, and the supports are designed to stabilize the part during the building, and the translator we use to convert the CAD data into a still file. And we are using the control unit sizes just for slices of thickness from 0.025 to 0.5 mm thick. And optical systems are used to direct and focus the laser beam. Means if we have some scan for different structures, so optical systems are uh, used for to give that scan direction, or we can say beam orientation. We are using the optical scanning system for that. And the elevated table drops enough to cover the solid polymer with another layer of liquid resin. And we are also having a leveling wiper or a vacuum blade that move across the surface to record the next layer of resin on the surface. Means if one layer is deposited on any surface, or any you can say uh, any part. So after to record next layer, we have a vacuum blade, or we have a leveling wiper. So that will wipe down a second layer on it. And after that, that laser will moving, and it will cure it. And after that, the part, then elevator will down that particular product, and then it will be again and again process. Means the laser then draws the next layer. It will continue process till we get the final product. And the application of this is, it is basically be used for the models for the conceptualization, packaging, and prototypes for the design analysis, verification, functional testing. SL is basically being used in the starting for the uh, prototyping. So we just named it as a rapid prototyping. And for the you can the patterns for the investment casting, sand casting, molding, and the tools for fixing fixtures, and the tooling design and the production tooling. Now I just talk about the SGC. Basically, this is a solid ground curing. The parts are built layer by layer from a liquid photopolymer resin that solidifies and export to UV layer. Here we are using a UV light. First in SLA we have used the lasers, so the lasers are quite expensive. So after that we move to the UV lights, ultraviolet light. They are also expensive, but it may be they, when the researchers are want to check that what actually happens when we are using the another means source for energy. So multiple parts can be processed in the UV lights. That is the advantage of it, and built in a parallel by grouping them in the batches using the cubital proprietary software. And each layer of multiple layer and contain cross-section slices of one or many parts. And the process is self-supporting, does not require the addition of any external support in it to the emerging parts, since continuous structures support for parts is provided by using the wax. Means we are using the wax for the support structures. Uh, these are the basically the principle for the cubital solid ground curing. Means we have to mill that basically we have some spray resins and we just develop the photo mask and expose that mask by the UV light source, and after that we have some vacuum uncured resin. Means if there's some uncured resin, uh, we just remove it by using some vacuum cleaner kind of thing, and then we just spray a wax for support structure, and after that we'll mill. We just do the milling for the flat region. And SGC system is produced by the Cubital Limited. As I told you, that process is data preparation, marks generation, and model marking. These are the data preparation, and you can see over here that what actually the cycle is followed by the solid ground curing. That the image of a layer, as you can see in the first, the image of a layer is produced using the toner on a glass plate to create a photo mask. So first of all, we just create the photo mask, and then thin resin layer is applied on a flat workpiece. Then after that, both the line under the collimated UV lamps. So as you can see that a single layer, and that it is cured by a UV laser. And then after that, a layer by layer manufacturing is done by using the photomask. And then after that, we use to mill that product, and we can use for the final application. This is basically the mask generation. These are the various applications for that we can use for the conceptual design presentation, design proofing, engineering testing, functional analysis, and we can use the tooling and the casting application for the investment casting, also sand casting, rapid, tool-free manufacturing, and we can also use for the mold and tooling, medical imaging, is if we have some diagnostic and the surgical operations and the construction planning custom. We can use for the prosthesis design also, solid ground curing. Now we are using mainly direct and deposition or a selective laser melting process. And these are the solid object ultraviolet laser printers that are available. And so these are the laser printed. These are having the same process for these solid systems. There's nothing to talk about them more. I just move to the FDM now. It is the main process for the polymers. That is the main process that is being used nowadays for fused deposition molding, and this is the leading company, that is Stratasys, for the FDM. And the principle of FDM is based on the surface chemistry, thermal energy, and layer manufacturing technology. It uses three principles: that a material in a filament in a form of spool form is melted in a specifically designed head, which extrude on the model. And when we extrude it, it will cool down and then we solidify to form a model. And the model is built layer by layer, and like the other art machines, means FDM. What actually how it works, that it has a material in the form of filament and that filament is melted on by some specific design head, and head contains heater, so that we can heat it, the filament, and that molten filament, that part, it is extruded accordingly, whatever the shape we required. And as you can see that as you can see the principle of the for that particular process, that we have the build material spool, and it is a support material spool. There are two type of the spools are there, the dark blue one and the light blue one. And the support, this is the build platform and the form base. This is a build platform and this is a form base, and these are the support structures and these are the part manufactured. So we remove the support structure by some another technique, just like we use sometime wire radium, but that wire radium is mainly used for the metals. But for polymers, we can directly hammer it and remove it. And the support structure filament is there, and build material filament is there. This is the extrusion head. These are the drive wheels, and the drive wheels mainly work on the you can say the numerically controlled. They are numerically controlled drive wheels. Means how much build filament we required or how much support filament we required. They will work accordingly. And then we have the liquefier. Liquefier means we have molten material in it, and these are the external nozzles. And if we talk about the process, the geometric model of a conceptual design is created by the CAD, which uses IGS or the STL formatted files, but mainly we are using the STL file format. and it is then imported into the workstation where it is processed through the quick slice. Means we have to slice down any solid product. Means if we have some STL file with us, then we have to slice it in a layer. So they are the different software, just like Slice TR and Quick Slice. There are many other software. They are open source, and with this software, the CAD file is slid into a horizontal layer after the part is oriented for the optimum build position, and any necessary support structures are automatically detected and generated. And that slice thickness that can be set manually to anywhere means between 0.172 to 0.356 mm. Means FDM is having layer thickness range between 0.172 to 0.356, and this is basically depending upon the need of a model, and sometimes it is also dependent upon a material and the condition in which we are working, and a tool path for build process are then generated, which are downloaded to the FDM machine. And we're talking about the process that is continuing the process, and the molding material is in spools that is very much like a fishing line, and the filament of a spool is fed into external head and heated to a semi-liquid state and sometimes to a liquid state also, and the semi-liquid material is extruded through the head and then deposited in the ultra thin layer from the FDM head from one layer at a time. It's just like a I have told for the selective laser sintering. Yeah, it is same with the selective laser sintering. The air surrounding the head is maintained at a temperature below the material melting point, and exiting material quickly solidify. Hence, if we have some molten material, that will quickly solidify it, and after that we just put second layer on it. It will solidify, then with third layer on it. So it is done for a particular product. Moving on the XY plane, the head follows the tool path that is generated by the quick slice, generating the desired layer. And application, we just talk about the FDM application. It is used for the molding for conservation and presentation, and prototype for design, analysis and functional testing, and patterns and masters for tooling. But FDM now being used for making small plastic parts or polymer parts for various components in the aerospace and the aircrafts. If there's some other polymer material, so they are using, mainly aircraft industries are mainly focusing on this 3D printing processes, because we can manufacture the complex kind of structure, or we can make intricate shapes, so that the strength to weight ratio will be same, and uh, strength to weight ratio will be high for these from these 3D printing machines. And when we talk about the selective laser sintering machines, in this particular sintering in this particular process, they are quite difficult, quite different from the FDM machines, because in FDM machines we used to heat the means any polymer, and if we have the melting point above the 500 or 600, that it is quite difficult for the FDM machine to melt down that particular material. So we have to use some energy source that are having high energy source. So we are using lasers in that. We can use electron beam also, and the part are built by sintering when CO2 laser beam hit a thin layer of a powder material. Means we have uh, powders, and that is in the form of a layer. Means we have a thin layer of a powder on a substrate plate, or on any table. Suppose we have a table and a powder is fed on that particular table, and the CO2 laser will hit that particular powder, and CO2 laser will follow the path, uh, will follow the same path that is given by the NC, is numerically controlled tool, and they will follow the same path. And the interaction of laser beam with the powder raises the temperature to the point of melting, and the resulting in the particle bonding and diffusing of the particle to themselves and the previous layer to form a solid. In the selective laser sintering, we just sintered. We do not completely melt down that means the powders. And the building of part is done layer by layer, and each layer of the powder process contains cross section of one or many parts, and the next layer is then built directly on the top of the sintered layer after the additional layer of powder is deposited via roller mechanism or on the top of previously formed layer. Means we use if we have some powder fed and after they get solidified, we use a roller to fed another layer of a powder, or we use a blade to fed the powder on the first layer or the previous layer. And the circular sintering process create three-dimensional object layer by layer from the CAD, directly from the CAD using the powder material with the heat generated by CO2, and the CAD data in the HTML format are first transferred to the system where they are sliced, and the sliced part means then after the slicing, SLS process starts and operates as follows, as it is given over here. As you can see that it is a laser power source. It is the this is the diagram for selective sintering and selective melting also, but the difference is that in sintering we have temperature lower than the melting point. uh, as you can see over here that we have a laser and these are the lenses, and this is the XY scanning mirror, and we can just control the laser scan path by the XY scanning mirror. And this is the laser beam that is impinging on the powder that is fed on a you can say a table, or you can say a powder bed. And after a single layer feeding, it is being means it will be melted by the laser source, and after the laser source will melt down a single layer, the second layer is fed by the leveling roller, and we have powder feed piston, means we have powder feed piston also, and we have two powder feed systems from here and from here, and these are the build pistons. Build pistons, the work of build pistons and the build chamber is there. Build pistons are present in the this build chamber, and the work of the build piston is there that it will lower down by a layer. Means if we have some manufacture some layer, then it will lower down that, just like elevator we have seen. So they just lower down a powder bed by a single layer thickness, and after that, leveling roller will level that powder again, and it will solidify again, and then after that, build piston will lower down again. So it is a process, means uh, again by again, and after that we get a final product in it. And based on the process, a thin layer of, as written, I have told that uh, heat fusible powder is deposited onto the part building chamber, and it is a bottommost cross-sectional slice of the CAD part under fabrication is selectively drawn or sent on a layer of a powder by heat generating CO2 laser, and the interaction of laser beam with the powder elevate the temperature to a point of melting and fusing of the particle to form a solid mass. And the intensive laser beam is modulated to melt the powder only in areas defined by the part geometry and cross section. And after that, as written over there, step 2 and 6 are repeated. Means we just repeat these steps. And I just talk about the post processing of the AM parts. Uh, the post processing we required, the first post processing we required to enhance the component, I can say the properties. First one is to remove the support material removal, and it is quite, you can say, uh, it is a point of concern that how to remove that support material. Means if we have some support material in it, how can we remove it? If we have some hammer, then it may also it may be chance that it will create a defect in a part also. So we have to use some support material that have a lower melting point, so that we can melt down that. Suppose we are using the wax, then we can melt down easily and remove it. And we have some surface texture improvement also. Just I have told you, the laser shock peening. The laser shock peening is basically used to for the surface treatments, and we can give some laser textures also, and accuracy we can also improve by the lasers, and the aesthetic improvements, and the preparation for use as a pattern, and the property enhancement using the non-thermal techniques. Just non-thermal techniques, just like the uh, you can say the short pinning. Short pinning is a non-thermal technique, and we can enhance the property by that. And we can also property enhance by the thermal techniques, just like you can do aging, or you can do solution treatment of any AM parts or any part. Uh, I'm just talking about the AM parts, but we can do for any parts the solution treatment, because these are the post-processing techniques we can do for any material. That is basically depend upon the material, that how much solution treatment we require, for how much time, and for how much temperature we require. Just like same for the aging processes. And support material removal के बाद, if we just talk about the support material removal, the support material can be classified into two categories: that material which surround the part as a naturally occurring byproduct of a build process, and rigid structure which are designed and built to support or restrain or attach the part being built to build process. Synthetic supports. So natural support processing process, synthetic support removal, support made by the build material also, support made by the secondary material. So that will depend upon the material, as I told. And post processing of the AM parts, and these are the support material remover. As you can as you can see or hear that when we manufacture these parts, these are the unused powder that will remove by the vacuum cleaner. That these vacuum cleaners are some specified vacuum cleaners because the powder size is very low. Uh, so it is quite difficult for a normal vacuum cleaner to clean this particular process parts. So support material removal, and you can see the uh, post processing of these kind of thing. These are basically the lattice structures, and you can see for the A part, FDM part courtesy of the gym flowers, and second one is a SLA part. Means this part is manufactured by the FDM and this part is manufactured by the SLA, and these are flat FDM parts. So these parts require some means post processing, means support material removal, because they are having some overhanging material in them. And when we talk about the surface structure improvement, so AM parts have common surface structure features that may be need to modify for aesthetic or performance reason. And common surface structures are stair steps, powder adhesion, means we have some to fill some patterns from the extrusion or beam based system or witness marks. So we can just improve the surface structures by them. And post processing utilized for surface texture improvement is dependent upon the desired surface mesh outcome. And when we talk about the accuracy component, so how can we improve our accuracy? There's a wide range of accuracy that is capabilities in the AM. Some processes are capable of sub-micron tolerance, whereas other have accuracy of around 1 mm. If we just talk about the solid materials, so they are having accuracy of nearly 1 mm, but when we talk about the laser melting process, they are having the accuracy of nearly microns, sub-microns tolerance. And typically the larger the wet volume and faster the build speed, the worse the accuracy of a particular process. Means if we have some very high large build volume of any product 3D component and we just increase the speed of a laser, uh, that is quite difficult for it to melt that particular powder uh, and the deposit in a very regular fashion, but it's quite difficult for it. So it will just melt a bead, small bead, uh, means on the substrate. So it will worse the accuracy of that particular process. Now the preparation for use as a pattern, often the part made using AM are intended as a part for investment casting and sand casting and room temperature vulcanization and the molding or spray metal deposition. And the accuracy on the surface finish, when we talk about the AM process, will directly influence the final part accuracy and surface finish. And as a result, special care must be taken to ensure the parts has the accuracy and surface finish desired in the final part. If we do not get means surface finish in them, then we have to uh, short pinning. We have to do some short pinning for the means AM parts so that we will get some surface finish in them. In addition, part must be scaled to compensate for any shrinkage that take place in the pattern replication steps. So you can see for the just like the aesthetic improvements as over SLA part before and after, means we have to do some plating, means chrome plating. This is a plastic part and we just put a chrome plating on it. So we can do this kind of post processing on the M parts. And preparation for user pattern often, and the property enhancement for the non-thermal techniques, told for the thermal techniques. And what are the guidelines for the process selection? Means how we just select that process according to the Wohlers and Associates. These are the uh, you can say the topmost leader now in the additive manufacturing process, Wohlers and Associates. And these are parts from the additive manufacturing are used for a number of processes, including visual aids and presentation models, functional models, fit and assembly, pattern for prototyping, tooling, pattern for metal casting, tooling component, direct digital and rapid manufacturing. So we have to means we have to set our guidelines, and that what process we have to select, that is depend upon these number of processes purposes. And we have to select a method for a part. We have the decision theory, means if we have a three element of any decision: option, expectations and preferences. Means Options means the item from which the decision maker is selecting, and expectation is of possible outcome for each option, and preferences means how the decision maker value each outcome. And how can we approach to determine these feasibilities means, and identify suitable material and process to fabricate a part is complex means. And the main advantage of this particular process is complexity, but also the customization means, if suppose that anybody is having and meet an accident and it have to uh, implant, if it will require an implant in the body, so you can you can fabricate a 3D, means you can make you can fabricate the your product by the 3D manufacturing process means a tibia or a femur, whatever you require, you can just manufacture by the 3D manufacturing process, and it will be highly accurate means. If you require some customization in it, then you can do for by using the 3D manufacturing process. It is quite difficult by the other processes. So these are the guidelines for selection and scenario. And just create format, the guidelines, examples. Now let's talk about the AM application. These are the main part, that is what is application. It can be used for the functional models, it can be used for the pattern for the investment, the vacuum casting, and it can be used for the medical models. It can be used for the art models also, because if we have some 3D scan with us, so we can convert that 3D scan into a CAD file or directly into a STL file, and that STL file will directly use uh, to manufacture the 3D model. And we have engineering analysis model. If suppose that you require to check the some strength in any material, so you have some make a model of it, and then you can just analyze on it. And rapid tooling, new material development. If you want to develop some new material, so you can develop very easily by the additive manufacturing process, because it give you a chance that the to means you are it give a chance to alloy different elements. So it is quite difficult with other materials. If you want to go for some casting process or some other process, it's quite difficult for developing a new material or new alloy. And we can use the bimetallic parts. Means bimetallic means we have two metallic parts of different materials, so we can use here, because uh, it is just like a welding kind of thing, so we can use the bimetallic parts over here. And it is also used for the functionally graded materials, means we can use 3D printing for the functionally graded materials. Uh, these are quite difficult by the other manufacturing process, and we also remanufacturing process. And reverse manufacturing is also possible by the additive manufacturing, because if you just reverse manufacturing, if you have some component and you just 3D scan that component, and after that 3D scan, you just convert it into a STL file, and STL file can be directly being used to uh, manufacturing the 3D component. And the application example of the for this is aerospace, defense, automobile, biomedical, and general engineering industries are nowadays are use these AM applications. General Electric have just recently planted one additive manufacturing plant in Bangalore for that means for the laser sintering process and the laser melting process. And shoe industries also means they are also using this additive manufacturing process, because as you know about our the shoe sole, that is quite heavy. So if we require same strength with reducing weight, so we require some lattice structures in them, or we have to means create some holes or intricate shapes in them. So that is not possible by any other processes rather than by the additive manufacturing. For Adidas, Nike, they are using additive manufacturing process nowadays just to make their soles, and they are also available in the market. And if we just talk about the application in the medical industries, as I've told, if we have some implant, as we all know that we have a different morphology for our head, means our body have different morphology with uh, other one body. Means if some person is having means you can say a large head, if and other person is having a small head. So in previous years, what happened actually, the doctor will implant the same means cranial. If you have some cranial injury with your head, so they just plant the single implant they have, means they uh, don't take care of that the means the patient is having different shapes, or they are having the different morphology of their body parts. So there will be chance that it will be not fit in your body, and it will create sometime a cancer, or we have to go for a second surgery uh, for the body implants. So just to remove that, uh, we have customization in the medical industry also. Means if you have some defects, or you have some crack in your leg, so you just scan it, and uh, just convert that scan file into a still file, and just directly manufacturing that, means your material by the 3D printing process or RDT manufacturing process. So this is a computer tomography that is used for the that is being used in the medical industry. And if we just talk about the parts of the metals, we have to use 3D scanners, as I have told, for the 3D printing used to make a skull with vascular tracks in the dark color, or the bone tumor highlighted using ABS. Means if we have bone tumor, then doctor will uh, remove that tumor and will put hydroxyapatite, means implant in your body. And the object connects process showing vascularity inside of human organs. So these are the AM process that is being used in the medical applications, and these are the different AM applications. As you can see, the perfume bottles with different capacity, cast metal and RP pattern for sand casting, investment casting for fan imprint from the RP patterns, as you can see. Thank you so much for listening me.
Thank you, Tarun. Thank you. Actually, there are a few questions I think people would be like to ask. Uh, just give me a minute. I'll go to YouTube and I'll check. Uh, Hello, Tarun. Can you hear me?
Uh, yes, sir, please.
Uh, Tarun, there is one question related to the slicing. What are the other tools? Like you said that there are certain softwares. So, is
Mhm.
there any other tool that we can use for slicing?
Slicing, we can use the Slice 3R software, that is, no?
It is a software. So, that
Open source
software.
software. It is
So,
open
all
source software.
so, is there any like limitation? Like if we have a certain 3D printer, with
Mhm.
that 3D printer, is there any slicing software accompanied with that 3D printer or something like that?
As I talk about the Slice 3R, it can be accompanied in any systems. Means if you
Any
have some any system, and they are the different software. They are being used by the different companies according to their this uh, what means how they require that particular slicer. Then accordingly they will fit in their systems.
okay. I think there is one question: how this method is useful in COVID situation in the manufacturing industry?
In COVID manufacturing process, in the COVID situations, we can use mask. Means we just print in our college also. We print the mask. Means you can say the shield, face shield. We can print by using the 3D printers. So it will be lightweight. Means if we just print it by some other manufacturing process, so it is quite heavy. Means it is quite difficult to means uh, take care for that mask. So we can means we can manufacture means mask with the lattice structures. So uh, it will have less weight with the same strength that required.
Sir, one last question: what are the limitations of AM?
Limitation of AM, as I have told, that it cannot be used for the large parts. AM cannot be used for the very large parts.
And what about the time? Whether the time required for the AM, I think, is a little higher on the end.
Yeah, but it will reduce the lead time. Means if we just talk about the lead time, means if we have some, uh, if you just go for the subtractive manufacturing process or the conventional manufacturing process, first of all you require the casting, then you will require to go for the CNC. So that will lead time will be reduced in this additive
So lead
manufacturing
time
process.
is reduced.
Hmm.
Okay, thank you, Tarun. Thank you so much. I think most of the people are saying that the presentation was excellent. We thank you for giving us the time and your valued knowledge for us. Thank you so much.
Thank you. Thank you so much, sir.
Thank you.